This is Jack Jackson with part 7 of our series of lectures on probability. This lecture is on independent events. Let's begin by recalling our definition of conditional probability. The definition of conditional probability of A given B is the probability of A intersect B divided by the probability of B. Notice that the probability we put in the denominator here is the probability of the event that we know has occurred, the given event, which is the one on the second event listed here in this notation. Multiplying both sides by the probability of B, we get probability of A intersect B as probability of B times the probability of A given B. Similarly, probability of A intersect B can be shown to be the probability of A times the probability of B given A. These two expressions are called the multiplication rule. Notice that we're multiplying a standard probability times a conditional probability to find the probability of the intersection. By the way, notice it's the one that's given here that is the standard probability in front. Standard probability of A, then we needed the probability of B given A to get that intersection. This is true in general. Now we're going to look at something that's not always true in general. We want to look at some special relationship that two events might have, and that is that they could be independent. So two events are independent events if they do not affect each other. So A happening or B happening, one of those happening doesn't really affect the other one. So the probability of A given B is the same as the probability of A. It's also the same as the probability of A given not B. So if we know B has happened, we can get a probability of A from that, given that B has happened. But if we do the probability of A given that not B happened, or just the probability of A happened and we don't know whether B happened or not, all of those three probabilities are the same thing. So these things are independent. A is independent of B. Similarly, we get the probability of B given A is the probability of B, and the probability of A intersect B is the product of the probabilities of A and B. Normally, remember that this is not true on the last one. Normally, you have to multiply a probability by a conditional probability to get a probability of intersection. But if they're independent, you can just multiply the two probabilities. Let's take a look at these conditions a little bit more carefully. Actually, all three of these conditions are equivalent, so we can take any one of these to be our definition, and once you get one of these three, you automatically get the other two. So, for example, let's look at the first one. The probability of A given B is the probability of A. Let's suppose we know that. Then the probability of A intersect B is the probability of B times the probability of A given B. But the probability of A given B is just the probability of A, so we have the probability of A times the probability of B. So we have the third condition. So we've shown if you got the first one, you've got to have the third one. Similarly, we'll show that if you got the second one, you've got to have the third one. So I'll take the second condition. Again, we start with probability of A intersect B, but this time we rewrite it the other way as probability of A times the probability of B given A. But again, probability of B given A, this is what we're given here to be the probability of B, and once again we get probability of A times probability of B, showing that the second condition implies the third one. Now we're going to show that the third one implies the first two. So we can start with any one of the three and get the other two. So if we have the third condition, let's take probability of A times probability of B is the probability of the intersection. We know that. And we can replace the probability of the intersection with probability of B times probability of A given B. But now let's divide both sides by the probability of B, cancel that out, and we see the probability of A is the probability of A given B, and the first condition is true. Similarly, we have the probability of A times probability of B is the probability of the intersection. This time replace the probability of the intersection by probability of A times the probability of B given A. And this time we're going to divide both sides by probability of A to get that to cancel out, and we got probability of B is the probability of B given A, which is the second condition. So we've shown that we can start with any one of these and go from it and prove the other two. So any one of these conditions is equivalent. Any one of these can be taken as the definition of conditional probability. So B is independent of A is also independent of B. So which one of these events are independent, and which, of course, if it's not independent, we'll call it dependent. So drawing a blue ball from an urn on the first draw and then drawing a red ball from an urn on the second draw with replacement. So we're replacing the balls before we make the second draw. Is that dependent or independent, and why? And the second situation is we're drawing a blue ball from an urn on the first draw and drawing a red ball from the urn on the second draw, but this time we do it without replacing whatever ball we drew the first time. Are those events independent? Think this over, get an answer, and then come back. Press pause now. Okay, now that you've thought this over, I hope you'll have seen that when we do this, drawing the balls from the urn with replacement, that's independent. The probability of a red on the second draw is the same as the probability of a red on any time we draw it. And it's the same regardless of whatever color was drawn on the first time. On the other hand, if we do this without replacing it, drawing a blue ball from an urn the first draw and then drawing a red on the second, are dependent events. In fact, drawing the red on the second draw, whatever that probability it is, depends on what color was drawn the first draw. If we draw a red on the first time, notice then the proportion of reds that's in the urn on the second draw is less than it was on the first time, and so the probability of red is going to go down from what it would be just drawing it the first time. On the other hand, if we draw a non-red the first time, then the proportion of reds in the urn is actually going up. The reds stay the same, but the total number goes down, so the proportion goes up, therefore making the probability of drawing a red the second time a little higher than just drawing a red the first time. So, the probability of drawing a red depends on what we drew the first time. And so if we knew we drew a blue ball the first time, we would have some extra information that would allow us to modify that probability of drawing a red the second time, and it would either be higher or lower depending on what we drew the first time. Like if we drew a blue the first time, that probability of drawing a red the second time is actually a little bit higher than what we drew than drawing a red the first time. Remember up here, drawing it with replacement, replace the ball every time, then that's independent events. Without replacement, that's going to be dependent. Which of the following events are independent? Making an A on test 1 and making an A on test 2. And then flipping a heads with a fair corn on the fourth time if we flip a heads the first 3 times. Think this over and come back in a second. Press pause now. Okay, well, making an A on test 1 and making an A on test 2 are dependent events. The probability of a student making an A on test 2 is higher if the student made an A on test 1. They've already demonstrated an A on test 1. They've already shown that they are a little better student, plus knowing the material better on test 1 is going to help increase the probability of a higher grade on test 2. So these are dependent events. Notice that being dependent doesn't mean that it guarantees the second event. So, for example, making an A on test 1 does not guarantee an A on test 2, but the probability will be higher for those students who made A on test 1 than it would be those students who didn't make an A on test 1. Flipping heads with a fair coin the fourth time, given that we flipped the heads the first 3 times, is independent. The whole idea of a fair coin is the probability is 1/2 every flip, regardless of what came before. Some people make an error in judgment here when they think about this, and they'll say, "Oh, well, some people may say, well, we've had 3 heads in a row. We're due a tails, so the probability of tails is increased." Well, no, it's not. It's still probably 1/2 every time. They're independent. Which of these events are independent? Making an A average on test and making an A average on homework in this course. Or, another one, rolling a 5 on a die and rolling a 5 on another die when you're rolling a pair of dice or maybe 5 dice. Take 2 particular dice and see rolling a 5 on one and rolling a 5 on the other. Think this over and come back in a second. Press pause now. Okay, well, making an A average on tests and making an A average on homework are dependent events. The probability of an A on average on tests is higher if the student makes an A average on homework. Making an A average on homework doesn't guarantee an A on tests, nor does making an A on not making an A on homework prohibit you from making an A on tests, but you're much more likely to make an A on the test if you've made an A on all that homework, because you've, number one, you've demonstrated that you've known it, but more importantly, you've done the practice to figure out what you need to know to do better on the test. And rolling the dice is independent. Rolling a 5 on one die has really nothing to do with rolling a 5 on the other die. Each outcome is uninfluenced by the outcome of the other die. So those are independent events. Now, here's another way to look at simple probability. If you've got a finite sample space, the probability of A is the relative frequency of A in the full sample space of S. So suppose we're just picking a point at random from the interior of this large rectangle, and notice that probabilities now are proportional to the areas. So the big rectangle is the sample space S, and the shaded green area is the event A. And in this case, you can see, I think, that the probability of A is going to be 1/4, because that's 1/4 of the total area of S. The area of A is 1/4 of the total area of S. Of course, this is just a simple probability, has nothing to do with event B. Now, let's look at a conditional probability. So notice back here, what we've done is we're going to look at the probability of A given B. So what we do is we restrict this to only take the information that's inside B. So we're basically going to erase everything that's outside of B. And when we do that, we're left with this picture. And so now we're looking at the A intersect B, or A and B, and we want to find the area of that region divided by the area of all of B. In other words, the probability of A intersect B divided by the probability of B. And so in this case, it turns out to be 1/6. So notice that that proportion is usually different. Over here, A, the probability is 1/4 of the total area here. The area of A is 1/4, so the probability of A is 1/4 if we don't know any other information. But we're given information that it's in that we're inside of B, then we get some more information, and that allows us to modify our probability. So the probability is not 1/4 anymore. Now it's dropped to 1/6, because A intersect B is only 1/6 of the area of B. Now, if you've got independent events, though, you've got a very special setup. You've got a setup where the proportion of A inside of S is the same as the proportion of A intersect B inside of B. So notice that in this picture, A makes up 1/4 of S, but in this picture, B's been modified from the last one, so that now A intersect B also makes up 1/4 of B. And so we look at the picture on the right, or restrict our picture to the middle part here, restrict our attention to B, which is illustrated here, which is also over here on the right, and that is the probability of A intersect B is 1/4, because probability of A given B is 1/4, because A intersect B is 1/4 of the area of B. Whereas the probability of A is the probability of drawing from the full sample space. So it's the area of A divided by the area of this whole S. And that turns out to be 1/4 as well. This is the special relationship that we have when we have independent events. Now, also, we can look at independent events. Remember, they're independent if and only if the probability of A intersect B is the product of the probability of A and the probability of B. So what if we have one of these two-way contingency tables? So we've got sort of two ways of partitioning the sample space. We've got events A and B, and we've basically got A and not A, and then B and not B. So if we go back to our visual over here, we've got A, green, and not A, white. We've got B, what's inside B, and not B, which is what's outside here. So we've got these four regions we're going to look at, but then of course they overlap. We've got A and B, that's this part right here, or this darker green area right here, that's A intersect B. We've got A intersect not B, that's the lighter shaded green area out here. We've got not A intersect with B, that's the part that's inside B but it's not shaded, this part right here. And not A intersect not B is this part out here that's in S but it's not in either A or B out here. So we've got these four different regions and they're indicated by the part of the table that's purple here. Now, these four regions are non-overlapping, they're mutually exclusive. So we can add up the probabilities across. So we can add these two probabilities on this row here, the B row. You can add up these two numbers with the purple background to get the probability of B. And similarly, you can add up the numbers across the row here to get the probability of the complement of B, not B. And similarly, we can add going down the columns to find the probability of A by adding these two numbers in the first purple column and the two in the second purple column. We can add to find the probability of the complement of A. And of course, if we add all four of them, since it fills up the entire sample space, that's going to be a probability of 1, which is also I can find by adding down this column or adding across this row. So this is the same as a two-way contingency table that we looked at before, where we had, I think we looked at one with a comic book collection in one of these lectures before. So it's a similar kind of setup. Now, it's independent if we can multiply these probabilities of just A and B to get the probability of intersection. So if we take the probability of B here and the probability of A, we multiply those together to see where they come together in the table, and we get the probability of A times B is the probability of the intersection, which is this upper left corner of the purple region. The lower left corner of the purple region then is the probability of B complement times the probability of A. And over here in the upper right corner of the purple region, we've got the probability of A complement intersect B, and that's going to be the probability of B times the probability of A complement. And then down here we're going to get the probability of B complement times the probability of A complement to get the probability of A complement intersect B complement. Notice if A and B are independent, then A and B complement are independent. And then A complement and B complement are independent, and A complement and B are independent. So all those different combinations work out to be independent, and so we can multiply those probabilities of the total column with the total row, and then get a probability of an intersection in the inner part of the table. So we're going to use this to help us do an example. So suppose we have an example here, and we're just given the probability of B and the probability of A. Probability A is 1/3, B is 1/4. Fill out all the missing 1, 2, 3, 4, 5, 6, 7 boxes here. There's 9 boxes altogether. I've only filled out 2 of them. You should be able to, from that, to fill out all of the rest of the boxes and the probabilities. So go ahead and do that now, and then come back in a second when you're finished with that. Press pause now. Well, notice if the probability of B is 1/4 and the probability of A is 1/3, we can multiply those where those two the yellow row and the yellow column come together, and we get the probability of 1/4 times 1/3 is 1/12 for the probability of A intersect B. Similarly, we can take the if we know the probability of A is 1/3, we know its complement has to add up to 1. So we know we have a 1 down here in this lower right-hand corner. So that means these add up to 1. So this is 1/3. This one, for probability of A, then probability of A complement must be 1 minus 1/3, or 2/3. Similarly, we can sum down the row to get 1, down this column to get 1, I should say. And so we got 1/4 is the probability of B, so the probability of its complement is 1 minus the probability of B. 1 minus 1/4 is 3/4. Similarly, these are independent, so we can take this 3/4, multiply it by the 1/3 to find the probability of the intersection there. So the probability of B complement times probability of A is the probability of A intersect B complement. 3/4 times 1/3 is 1/4. And then, similarly, to get this one here, we can take the 3/4 times the 2/3 to get 1/2. the 1/4 times the 2/3 to get 1/6. And of course it should check because 1/12 plus 1/4 is 1/3. 1/6 plus 1/2 is 2/3. 1/12 plus 1/6 is 1/4. 1/4 plus 1/2 is 3/4. 1/4 plus 3/4 is 1. 1/3 plus 2/3 is 1. 1/4 times 1/3 is 1/12. 1/4 times 2/3 is 1/6. 3/4 times 1/3 is 1/4. 3/4 times 2/3 is 1/2. So let's just pause for a second and check all of those. Make sure you can actually do that. Do those by hand and or check them with the calculator if you like, but make sure all of those things do check out. Press pause now. Okay, now we've verified that this table does work, and notice just knowing those two probabilities, we were able to figure out all of these missing probabilities. Let's try it again. This time we also know two things, but this time the two things we know are a little bit different. We know probability of B, and we know probability of A intersect B, and just for a change, we put them in decimal form this time. So let's figure out the rest of the probabilities in the missing boxes in this particular table. Again, A and B are independent. We can only do this the way we did this if A and B are independent. They were independent in the last example, and they're independent in this example as well. Go ahead and figure the rest of the table out. Press pause now. Okay, and so here's where they all are. Remember the ones we started with were 0.26 and 0.13. Of course, they must add up to be 0.26 going across, so probability of A complement is 0.26 minus 0.13, which is also 0.13. So we can figure that out just because they add up to 1 going across. And by the way, that has nothing to do with complementary events. That has to do with the fact that these are complements of each other. Now, let's go on down, though, and see if we can figure out what's going on. Well, we can also add down the row, and we know down the column here, and we know this is a 1 at the bottom. So if this is 0.26 for probability of B, we know the probability of its complement is 0.74. Now, we can figure out from that the probability of A. So we know the probability of the intersection, since they're independent, is 0.13, has to be 0.26 times the probability of A. So to find the probability of A, we just divide by both sides of the equation by 0.26, and we see the probability of A is 0.13 divided by 0.26, which is 0.5. Now, we know that these two add up to be 0.5, so 0.5 minus 0.13 is 0.37, and these two add up to be the 0.74, so 0.74 minus 0.37 is 0.37, and the probability of these two probabilities add up to 1, so if probability of A is a half, so is the probability of A complement. And now we have the whole table worked out, and let's just double check everything. 0.13 plus 0.37 has got to be 0.5. 0.13 plus 0.37 has to be 0.5 in the second column. The third column, 0.26 plus 0.74 has to be 1. Adding across has got to add up right as well. 0.13 plus 0.13 is 0.26. 0.37 plus 0.37 is 0.74. 0.5 plus 0.5 is 1. That really, those sums have to work because we're dealing with events and their complements. Those sums have got to work in these tables no matter what. But the fact that they're independent events also tells us we get some multiplication things happening. 0.26 times 0.5 is 0.13. 0.26 times 0.5 is 0.13 for the second one there. 0.74 times 0.5 is 0.37, and 0.74 times this 0.5 is 0.37 here. And so all those things should check out. Again, let's pause for a second and make sure that you're convinced that all those things do work out. Press pause now. Okay, so now let's take this same information and figure out the conditional probabilities. What's the probability of B given A and the probability of A given B by looking at this? Go ahead and figure these out now. Press pause. Okay, well, we can figure it out directly, and that is the probability of B given A is the probability of A intersect B divided by probability of A. Probability of A intersect B is 0.13. Dividing by the probability of A, we're dividing by 0.5. 0.13 divided by 0.5 is 0.26, but 0.26, notice, is the probability of B. Of course, once we knew it was independent, probability B given A was just the probability B. We could have just looked up here in the table and pulled it out. So likewise, we want to do the probability of A given B. It should be the same as the probability of A. It should turn out to be 0.5. Let's just double check. Probability of A intersect B is 0.13. We're dividing by the probability of B, which was the 0.26. 0.13 divided by 0.26, sure enough, is 0.5. Alright, here we have another example. This time we don't know ahead of time whether these events are independent or not independent. But this time I gave you not just 2 pieces of information, but 3. And from this we should be able to go ahead and fill out the whole table. And then when we're done, we're going to ask the question, are the events independent or not? So here we can't assume that they're independent to begin with. Do not assume they're independent. Fill it out based on other information, other properties in the table, and then check to see if it's independent or not. Go ahead and do that and then come back. Press pause now. Okay, well, to fill this out, we're going to use the fact that we can sum up things. For example, these are mutually exclusive events here for A and A complement. So 0.14, well, these intersections, A intersect B and A complement intersect B, are mutually exclusive. So 0.14 and 0.35 we can add up to get 0.49, and that's got to be the probability of B, because those are the only 2 events. We've taken B and broken it into 2 parts, the part of B that's in A and the part of B that's not in A, and that's all of B. So adding those 2 probabilities together gives us the probability of B, because once again there's no overlap of those 2 pieces. So those 2 pieces make up all of B, and there's no overlap, so we can just add them up to get the total probability of B. And of course that's 0.49. Similarly, we had 0.14 for the probability of A intersect B and 0.33 for the probability of A intersect B complement. Again, now we've taken A and we've divided it up into 2 pieces that comprise all of A, the part of A that's in B and the part of A that's not in B. That makes up all of A, but those 2 pieces don't overlap. So we can just add those probabilities to get the probability of A. So that's 0.14 plus 0.33 is 0.47, so that's the probability of A. Alright, so now we have all the first row and all the first column. Well, we also I have to have a 1 down here in the bottom right. So if the probability of B is 0.49, the probability of its complement is 1 minus 0.49, 1 minus the probability of B, and so of course that's 0.51. And similarly, the probability of A is 0.47, the probability of its complement is 1 minus the probability of A, that's 1 minus 0.47, so that's 0.53. And then finally we can get this last one here a couple of different ways. One is by knowing that these 2 add up to be 0.53, so 0.53 minus 0.35 is 0.18. We go down that column. Or of course we could have done it by going across the row either way. So now what we should see is the rows sum up correctly and the columns sum up correctly. 0.14 plus 0.35 is 0.49. 0.33 plus 0.18 is 0.51. 0.47 plus 0.53 equals 1. The columns have to sum up correctly too. 0.14 plus 0.33 is 0.47. 0.35 plus 0.18 is 0.53. 0.49 plus 0.51 is 1. So everything all lines up correctly. Now this has nothing to do with whether or not these events are independent. But now we can look back at the table and remember our other property that we know it happens if it is independent. Check and see if they're independent or not. Go ahead and figure this out and come back in a second when you figure it out. Press pause now. Okay. Well, no, they're not independent. A couple of different ways we can see that. For example, let's figure out what happens when we multiply probability of A and probability of B. That's 0.47 times 0.49. That's 0.2303. If it's independent, that should be the probability of the intersection of A and B, but the probability of intersection A and B was 0.14. In other words, we multiply this number on the first row here on the far right times the one on the far bottom on the first row together to get where that row and column intersect, and it didn't work out. So that means they're not independent. Or if we think about it in terms of conditional probability, what's the probability of A given B? That's the probability of A given B divided by probability of B. Well, probability of A given, or A intersect B, I should have said. Let me say that right. Probability of A given B is the probability of A intersect B divided by probability of B. So probability of A intersect B is 0.14. Probability of B is 0.49. Divide those two, it's actually repeating decimal, 0.285714. Actually, the whole thing's repeating. And so that turns out to be, well, it's not the same as the probability of A. Probability of A was 0.47, so those are considerably different there. And so probability of A is not the same as the probability of A given B, so A and B are not independent events. They are dependent. Okay, you wouldn't have to do both of those things. Either one of those things would be enough to show that the events were not independent. Alright, let's do some of the same stuff, but do it on a probability tree. So suppose we have this probability tree here, and there are three possible events the first time. Either one of these things has to happen, either event A, B, or C. And then we're going to do a multi-stage event where we're going to do the same sort of experiment twice, and again you can get an A, B, or C each time. Let's suppose that these are independent. If we look at these in pairs, they're independent. A and B are independent of each other, A and C are independent, and B and C are independent events. So use this to fill out all the probabilities, and by that I mean I've given you two of the probabilities on the edges. So the probability of just doing an A the first time is 0.6, the probability of B the first time is 0.15. You need to figure out all of these other probabilities. And remember, the probabilities on this second bunch here are conditional probabilities. And then we can use the multiplication rule to figure out the probabilities of each of the paths going all the way to the end. So fill out all the rest of those probabilities if you know that these are independent. So go ahead and do that now. Press pause now. Okay, now we're back, and you should have probabilities. You should have a probability here, one right here on the probability of C, and then you'll have these 9 probabilities figured out here, and then 9 probabilities at the end. If you don't have all of those probabilities, that's 19 numbers that you have added to this this tree. If you don't have all 19 of those, press pause and go back and do them again. But by now you should have those. So how do we figure that out? Well, first of all, let's figure out this one for probability of C. Since these are all the possible events, and there's no overlap of A, B, and C in these trees, that we have 0.6 and 0.15, and whatever this probability of C is must add up to be 1. Well, 0.6 and 0.15 is added together as 0.75, and so you can do 1 minus 0.75 to get 0.25 for C. And since these are independent events, it doesn't matter what happens the first time. The probability of doing an A event, whatever that is still 0.6 the second time you do it. And the probability of B the second time is 0.15, and the probability of C the second time is 0.25. In fact, it doesn't matter whether you do A, B, or C the first time. You get probabilities 0.6, 0.15, 0.25 for A, B, and C respectively on the second thing. So the second part of it looks the same, and of course those 3 probabilities add up to 1. Now how do I figure out these ones at the end? Well, just multiply. So the probability that we get A both times is 0.6 times 0.6, which is 0.36. The probability A first, then B is 0.6 times 0.15. Probability of A, then C is 0.15. Notice that this case, also the probability of B and then A is the same as A and then B. We've got a 0.15 times 0.6 or 0.6 times 0.15. Either way, it is the same. That's the 0.09. And similarly, we can go down here and fill out the rest of this tree. Very similar to what we were doing in the tables. Now we're just putting the same information and the same techniques into a tree. Once again, we're assuming we had some independent events here. The independent events is what will allow us to know that these probabilities were the same the next time as they were the first time. That's what allowed us to finish the tree. So now we have events A, B, and C. And those are all 3 events that can happen the first time. And then notice we have D, and really D complement is E. So if D doesn't happen, then E happens. So that we get an E complement. So we have a probability that A happens and then D happens in that order is 0.08. We have the probability that A happens on the first step is 0.2 and that C happens the first step is 0.3. Use that information to fill this out, and we're assuming that event D is independent of the events A, B, and C. So go ahead and finish this. Press pause now. Okay, so the first thing we can do, regardless of whether D is independent of A or not, we know that this probability point is going to be 0.4. Why? That's the probability of D given A, and we know that if we multiply that number by 0.2, we're going to get this 0.08. So how do I find that? Well, I just take the 0.08 divided by 0.2, and that's how we got the 0.4. These two probabilities here must add up to be 1, so that means that probability is 0.6. Now, if this is 0.4 and 0.6, if they're independent of A, B, and C, then they're 0.4 and 0.6 every time. And I think we had two of these probabilities and not the third one. Let's see, which one was missing? The one in the middle was missing. So we know that all three of these add up to 1. This is 0.2 and 0.3. That's 0.5, so that leaves 0.5 for the remaining amount. Once I have all of those, I can go back and I can multiply. 0.2 times 0.4 is 0.8. 0.2 times 0.6 is 0.12. 0.5 times 0.4 is 0.2. 0.5 times 0.6 is 0.3. 0.3 times 0.4 is 0.12. 0.3 times 0.6 is 0.18. And one check is that all these red numbers on the ends represent, they're all mutually exclusive because there are specific paths that are not through this tree that are not the same. None of them can happen at the same time. So these are probabilities that we can add up, and they add up to 1 because we've done all the possibilities. You can check that. So please check all those things. Make sure you understand this tree before you go on. So press pause now. Finally, I want to do one more thing in this unit, or this lecture. And sometimes students get a little confused about mutually exclusive events and independent events. These are absolutely not the same thing. In fact, if it's a mutually exclusive pair of events, they absolutely cannot be independent. They're absolutely the opposite of independent in a way. Because independent events, knowing A, if you've got A and you want to find the probability of A given B, if it's independent, then it's the same as the probability of A. So in other words, knowing B, whether or not B occurred, tells you absolutely nothing about the probability of A. But on the other hand, not only does mutually exclusive events, knowing B happen, tell you something about A, it tells you everything about A. If B happens, A doesn't happen. So the probability of A given B is not the probability of A. It's 0. It's very specifically knocks that probability all the way down to 0. So mutually exclusive and independent are two very different relationships. Mutually exclusive means if one event happens, the other cannot happen. That is very dependent. Okay, so mutually exclusive events are dependent events. Independent events can't be mutually exclusive. They have to have some other relationship. So there's a little bit of introduction to independent events.